Good afternoon, everyone. Can you see my share screen?
Yes, go ahead.
Yeah. It's honor for me to be here to present our recent book, namely Explainable transformer-based approach for ECG Anomaly detection. And this book was done with my supervisors from University of Leisure and University of Liên, and with my co-author from Đông Á University. Our presentation includes 6 tasks. I begin with the introduction and some related work and backgrounds, including the framework for anomaly detection and the sub-day editing explanation. And then the proposed explainable framework follow with the experiment on the real data set. And we end the presentation with perspective and conclusion. We know that detecting anomaly is very important in all aspects of life. It enables us to identify and address unexpected deviation from typical or expected behaviors, ensuring the safety, efficiency, and overall well-being. For example, in finance, detecting unusual transactions can help prevent fraud and financial risk. In healthcare, timely identification of anomalous pattern in medical data like ECG signal can lead to early intervention for potential life-threatening conditions. And the identification of anomalies has received much attention from both statistics and machine learning. For example, in statistics, control charts are powerful tools for effectively detecting anomalies and monitoring process. And we have some popular control charts that are often used, like the CUHAS, the QSUM, and other control charts. And recently, due to the increased availability of large and diverse data set and the advancement of machine learning algorithms, it leads to a growing trend toward developing the machine learning techniques for anomaly detection. And until now, numerous state-of-the-art machine learning models have demonstrated high accuracy in anomaly detection in various domains, like manufacturing, industry, healthcare, etc. Although the machine learning model achieve high accuracy, the challenges still remain, particularly due to the lack of transparency. For example, in healthcare, a model may detect anomalies in ECG signal, but without the transparency, clinicians struggle to understand why. In such sense, if the wrong decision can have serious consequences. And in cybersecurity, without clear reasoning for an anomaly, it's difficult to justify intervention or prevent attacks. So the transparency of the model decision is crucial because it's providing the explanation for prediction. It helps validate the model accuracy by showing which feature influence the outcome, and it allows to often inform decision making and ensure the decision are explained and justified. So in this book, we propose integrating sub technique into our previous proposed transformer-based EAI and SPDD charts to enhance the transparency in detecting anomaly. Specifically, we apply sub to the framework to analyze the reconstruction error vector obtained from the EAI to uncover which window in the ECG section significantly impact the reconstruction error. And this approach enhances our understanding of the model performance by firstly providing the global explanation, identify which window does contribute the most to our model, and secondly offering individual level explanation, determining which window impacts specific ECG instance. And then I will briefly describe the framework that we use for anomaly detection in ECG. Firstly, the transformer is crucial neural network architecture, and one of the core features of transformer is self-attention mechanism. It helps transformer to accept part of the input data in relation to every other part. So it enables a deeper understanding of the type segment. And the second core feature is multi-head attention. It allows transformer to focus on different parts of data at the same time and helping it understand complex relationships better. And transformer is widely used in natural language processing and various fields like time series and anomaly detection due to its efficient handling of several data for better predictive performance. And the very asynchronous encoder is a prominent generative model in deep learning. And the objective of EAI is to model the complex data distribution by introducing two key components. Firstly, the probabilistic encoder. It maps the input data to a distribution in the latent space, QP, and a decoder reconstructs the data sample from latent space, PT. So in encoder, VAE try to approximate the intractable distribution theta by another tractable distribution QT by minimizing the convex label event in equation 1 to ensure the similarity of the two distributions. And the loss function of variation lower kind of encoder is grouped to pass the reconstruction log and the convex label event given in equation 2. And in figure 1, you can see the general structure of EAE. And EAE has a lot of application, mostly in data generation, denoising, representation learning, and anomaly detection. And let's move on to MFI SPDD control chart. SPDD is one class classification algorithm used to detect abnormal observation by modeling the normal one. So it creates a spherical boundary defined by a center A and radius R around the observation. And MFI technique is applied to employ a memory-based approach in time series data, and the MFI vector can be calculated using the equation 3. The SPDD optimization problem to obtain a description of the data set using MFI-based vector given in the problem 4. Here C is a trade-off parameter that controls the balance between the volume of the sphere and the error. And if we have a new sample Z, the distance between this sample and the center of the sphere is calculated using the equation 5. And if this distance is greater than the control limit, then we can conclude that is considered like abnormal. And let's move on to start with additive explanation. This is a technique introduced by Lambert in 2017 to explain the output of any model in understandable way. SAP calculates the importance of a feature by comparing what a model predicts with and without a feature and average over all possible combinations of a feature. And it has a lot of application. For example, in finance, shortcut the bank understand why a loan will approve or denied by showing which factor was the most important. And in character doctor, you start to understand which medical factor lead to certain diagnosis, which help them explain the reason for the disease to patient. And this is the idea behind the SAP that I remember because due to the limited time. But here you can see that the SAP value can be calculated like in this equation. And for the framework for anomaly detection, we will use the reconstruction error vector extract from the VAE architecture, and we use the vector to train the MFI SPDD model. And the control limit of the control chart is computed using the bootstrap percentile approach, and it helps us to control the fail alarm rate. And this architecture has demonstrated superior performance in detecting abnormal signal in ECG data set without relying on the data distribution and reducing the fail alarm rate. And this is our proposed explainable framework for ECG anomaly detection. You can see here we have the data, we firstly pre-processing and then we feed into the transformer-based EAI, combined with MFIS PhD for anomaly detection. And we will integrate sub here to explain, to have a global and local interpretation of the reconstruction error. Next, move to the experiment. We use the real data set. It is a hybrid data set from the PhD, and it's combined the anomaly subject and normal subjects. And we randomly selected 5,000 Hz bits from the data set, and the data set is already pre-processing and was pre-labeled by the experts, with the label indicating the presence of specific Hz or the norm. And here is an example from the data set. The orange line illustrates the abnormal signal and the blue one is the normal signal. This is the result for anomaly detection. And move on to next slide. For more detail, this is a classification report for the anomaly detection framework. You can see here an impressive accuracy of the model. And we have only one misclassified from normal class as abnormal. And the framework can rely on prior data distribution knowledge, and it also contributes here fixed value for average run length of the control chart. And this is an example of the explanation by staff. It is the individual explanation. Here you can see the three windows that I highlight by the red color. The doctor can, when they have this figure, they can firstly check the window to predict the potential heart disease from the patient. And this is the second example. Similarly, the first example. With this example, the doctor can firstly examine the three windows highlighted by the red color here to predict, to diagnose the patient first. And this is a global explanation by the staff. And you can see that the window in the top of the plot are the ones that contribute the most to the output of the model. For the future work, we will integrate our framework into a federated learning for data privacy, and we start with the self-supervising technique. This is a technique has to learn from unlabeled data, and it has to reduce or rely on the labeled data. And we also study the one-person technique. This technique will have to reduce the model size and computation needs by compressing data and accuracy to single bits. And it is ideal for resource constrained IoT environment and federated learning testing. For the future work, we intend to integrate the self-supervised learning and one-person learning technique in deep learning model for IoT multi-various country data in federated learning for efficiency and accuracy in environment with limited label data. And for potential future work, we can have a collaboration with colleagues from Đông Á University For example, they are collecting the smart spectral data for enhancing anomaly detection algorithm, utilizing FPGA's resources for computational efficiency, or applying the EAI device for real boot testing, etc. And for conclusion, in this book, we have to introduce an explainable framework combining the transformer-based EAI for and SCDD control just for anomaly detection, and we use a fail alarms, and we integrate the SAP technique to this framework to provide the feature level insight, offering the global and local explanation for family contribution. And it enhances transparency in the model, and we test the proposed framework in a real SEC dataset, and the reference that we mostly use in our study. And thank you for the attention.